So, hello students. So, today we will continue our discussion on Poisson's process. Now, you recall that we define Poisson's process with three major property. One is independence property, independence property, and then uh, time homogeneity property. Okay, so time homogeneity property. And third property is called the small interval probabilities. Probabilities. Okay. And we already discussed the random variable one. This so we define number of arrivals in the time length tau. We define this is Poisson random variable already, right? Arrivals Poisson random variable. Okay, that already proved. And also we proved the time of first arrival. Okay, so this is exponentially distributed. Exponentially distributed, right? This is already proved. Okay, so now today we will discuss a few more important random variables. So the first one is interarrival times. Interarrival times. So you recall similar to Bernoulli process. So in a Poisson process, so you have a arrival and then another arrival, like that. Okay. So you already so this is my T1 and then T2, T3. Okay. And similarly, this is my first arrival time, which is Y1, and then second arrival time Y2, and so on. Okay, so in interarrival time we already learned that T1 is um, exponential random variable with parameter lambda, where lambda is the arrival rate of the process. Okay, so now we will use the fresh start property after arriving first arrival. It is now is again a fresh start. From the fresh start property, T2 is also a exponential distribution. So T2, T3, they are all independent, right? So independence property tells you that because of different time interval they are independent, and then fresh start property tells you that this is again a Poisson process. So they also satisfy the same condition, that exponential random variable. So this Ti is So all TIs, so thus phrase start property implies that all the TIs means interarrival times, are exponential random variable, right? And hence you can have a alternative description of the Poisson process. So you can give this alternative definition. So you can say that with these two following property, one is called one letter start with a you start with a sequence T1, T2, and dot 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 of um, IIT exponential exponential random variable, okay, with extra random variables, and you say that, and uh, let these stand for the interarrival time. Interarrival times, okay, and then you say that the arrivals are actually record an arrival, record an arrival at time so T1 first arrival, and the second arrival is T1 plus T2, and then T1 plus T2 plus T3 third arrival, and so on, okay. So if we have these two property, then also it is describe the Poisson process, okay. And now the next random variable you can attach is, with this Poisson process is the kth arrival time, okay. So this yk is the kth arrival time, which is nothing but t1 plus t2, and then the tk, okay, kth arrival time. And then you like to know that what type of random variable this yk. So this is question. So how yk distributed? Now let us see. So now you can easily find out the expected value of yk is nothing but, because ti's are independent, so these expected values are sum over expectation of ti's I equal to 1 to k, and ti's are you know that ti's are IIDs with parameter lambda, so, and also exponential. So this expectation of ei's are 1 by lambda, so this will be summation over 1 by lambda I equal to 1 to k, and the value will be k over lambda. Clear? Okay. So, and then obviously variance, you can find out the variance of yk will be, because IIDs are these are IIDs, so there is no covariance. So this covariance ti, tj, is 0 for I not equal to 0 j. So this is sum over variance of ti I equal to 1 to n, and hence this will be k over lambda square, right? Now you would like to know how, what is the PDF look like, how the PDF look like. Okay, so there are many methods, so I will compute one method. So the PDF of yk, how to find out the PDF of yk? So I will first find out the CDF of yk. So what is CDF? So you know that the CDF of yk is what is kind of say, write down if yk at some point say y, and this is nothing but probability that yk less than equal to y by definition. Okay, but what the, what is the meaning of the event this equal to yk less than equal to y? What is the meaning of this event, right? So I would like to find out the probability of this event, which will gives you the CDF of the random variable yk. But what is this event? So you see that this event is nothing but the number of arrivals um, so yk is less than equal to y. So what does that mean? That means in the time length 0 to y, there are at least k many arrivals. So number of arrivals between 0 to y is more than at least k, right? So number of arrivals in the interval 0 y is at least k. So this is greater than k, right? This is the meaning of this E, right? And hence so at least k means it can be k, k plus 1 and so on. So thus this probability of E, which is nothing but probability that say n is equal to k to infinity uh, yn, right? So you now recall that pyn is nothing but probability that n many arrivals are there in the time. um, so this is the length of the interval is y. Okay, so in the time length of interval y, the number, what is the probability that there are n many arrivals, right? Now p is nothing but n has to be at least k, so k, k plus 1 and so on, right? And this is nothing but same as 1 minus probability of n equal to 0 to k minus 1. Okay, n clear? And now you can easily find out this probability. So your if yk or y, this will be equal to 1 minus and so you now you call that pyn. What is pyn? So pyn is so this follows what is that this follows this Poisson process, this number of n arrival, right? Poisson process with parameters. So if the rate of the process is lambda and time length is y, then the parameter for Poisson process will be lambda into y, right? So this will be summation n equal to 0 to k minus 1 into lambda y power n into e power minus lambda y by n factorial, right? And hence you can find out thus the PDF of yk is given by, so this is if yk y, so it will be dy of if yk or y, right? Now you can do the integration easily. Sorry, you can do the differentiation easily. After doing the differentiation, the answer will be simple: y power k times k minus 1 e power minus lambda y factorial k minus 1, right? So is just homework. You can easily do this homework. Now this type of PDF or the distribution is called so this is called yeah, the Erlang distribution. Erlang is a name after Danish mathematician Erlang. Erlang random variables. Okay, and so note that this is actually, so here k is integer, right? It's the number arrival, so k is integers. So k then equal to 0. So which is the Erlang distribution is nothing but a special case of gamma distribution. You call gamma distribution k can be any positive real number, right? So which is a special case of the gamma distribution, which we already run in the class gamma random variable. Okay, so what we learned, so in Bernoulli process, the interarrival times, so you remember interarrival times are geometric, and the kth arrival time was negative binomial or Pascal. But here in Poisson process, interarrival time is exponential, but the kth arrival time is Erlang distribution, which is special case of gamma random variable, right? So this is two nice random variables which attach with Poisson process. Now we will learn something very interesting, similar to what we learn for Bernoulli process. So it's called splitting of a Poisson process. Okay. So you recall in Bernoulli process also we did splitting thing. So here also we can have splitting. So for example, so so the arrival is coming like somewhere, so where, right? Now when arrival is coming, so you can inside the arrivals of some certain things, so you can split into, say, this way, that a specific type of arrival you will keep. So this is the original process. So this is original. Now in the splitting thing, you can keep only this. So this is, you are not keeping here, but you are keeping this one, then this one, and then you are keeping, say probably this one. Okay, and then you are discarding the other one. So other one is this one, and then this one. Okay. So for example, so these are also with probability. Obviously, you are keeping this with probability, say p, and you are discarding these with probability 1 minus p. Okay. Our original process has read, say, lambda. Now question is that after doing this process, you are getting, say, these two new process, whether they are also Poisson process or not. And if they are, okay, so question, these two new process and process uh, Poisson or not. Okay, so this is a simple question. And if they are Poisson process, then what are the rate of arrivals in the each case. I mean the first one and second one. Okay. So these are natural question to ask. Okay. So for example, so let me give you an example. So suppose this um, say the GPO, the General Post Office at say Chandigarh. So they are receiving many things, right? So they sometimes they received letter, they received sometimes gift items, the packages, many things they received. Okay. So suppose they are receiving, say, so let me first consider the letters. So they are receiving letters through a continuous process, sometimes, like, and then sometimes, okay. And then they are distributing those letters. So there may be the case that few letters are actually for people of Chandigarh. So they just gives these letters, which are people of Chandigarh directly. Okay. So these are called sometimes we can say that this is called local um, local package, okay, or local letter, whatever. Okay. And sometimes okay, so local packet something, but sometimes some letter can come for Ropar. Okay. So they need to transfer this thing to Ropar area post office. Okay. So this is Ropar. This is Chandigarh. Okay. So something they are keeping for Chandigarh, something they are transferring to Ropar. Okay. So now see, now the process they split into two ways. Say maybe one is Chandigarh, one is Ropar, one is non-Chandigarh, whatever. So you can split this kind of process. Okay. Now question again, this whatever question you ask, whether this original process when you split, then the new process are also process or not. So there are many ways to check this. So first way is the definition. So you know the definition to check process. So obviously here first two properties are intuitive, like independence properties, independence properties automatically true because original process is independent. So the new split one also has to be independent. Okay, because they are the part of the original, and then time homogeneous property also. So these two are immediate. Okay. So this both this first property and second property is obvious, but you need to check whether third property, small time intervals, small time probability, small intervals probability. Okay, so first method. So how to check this property? So this is you. So you have, you know that rate, that arrival rate is lambda, and then you are keeping this arrival rate is lambda rate, but you are keeping in Chandigarh for rate probability p and discarding to 0 per 1 minus p or whatever the complementary thing. Okay. So in the first one, the local one, what happened? Local one, that probability that there is one arrival. So this probability that one arrival in delta small time delta was what? So lambda delta plus something, say higher order, right? Higher order terms. Now now in this is the uh, So this probability for the original one. Okay. Now the new one. So the probability is a new process where you are keeping local one, a local process. You can say local also. So let me write down L for stand for local. So the local letters which are made for Chandigarh. So what will the probability that there will be exactly one arrival? So that means in the time interval whatever it came, so that must be with probability p, that must be local. So this is lambda p into lambda delta into p, and then higher order terms. Okay. And then the vice versa, that other one. So again you can easily find, so this is the probability for local one, that one. And then similarly you can find out that zero arrival, probability for zero arrival for local one, zero arrival. Okay, this also you can find out similarly. Okay, so this is kind of intuitively you can understand that, but there is a rigorous way. There are many rigorous way of proving these things. So maybe I can give you a proof of rigorous proof. So let me give a the second method, the rigorous proof that the splitting of Poisson process gives you again Poisson distribution, Poisson process, right? So how to do it? So so let me start with that. Uh, Suppose some time you have some time interval, say tau, okay, and let say maybe L tau is the number of local arrivals, and in tau is the original arrival, is the number of total arrivals. Okay, so total arrival is n tau. So that is also we already know that n tau is and obviously the rate, I am assuming that lambda, rate equal to lambda, and we know that n tau is Poisson with parameters lambda tau. Okay, so that is known. Now we would like to find out whether L tau is Poisson or not. If it is Poisson, what is the rate? Okay, or what is the parameter? Okay, or what is the rate of the process, whatever. Yeah. So now how to do this? So the very important property to prove something, like if you want to prove L tau is kind of Poisson with something, and then it is enough to prove that the moment generating function of L tau or L tau is same as the moment generating function of this Poisson random variable, right? Poisson random variable. Okay, so that we need to find out. But what is, so now how do you describe L tau? So now let me describe L tau that so for say I equal to 1, 2, or in tau. So there are in tau many arrivals. So whatever I equal to 1 first arrivals and in tau many arrivals. So you define, so let xi uh, be a Bernoulli random variables which is 1 if this arrival is a local arrival, if so this is the ith one I am defining, right? If the ith arrival is a local arrival, okay, and 0 otherwise. Clear? So xi is taking values 1 or 0. So this is for local arrival. The ith one, local arrival. So this ith local arrival is 1, otherwise if not local arrival. Okay. So what does that mean? That means so thus, so with that definition, you can say that your L tau is nothing but x1 plus x2 plus dot dot x in tau, right? So out of in tau many arrivals, you have exactly L tau many local arrivals. So but you see that this x1, x2, xn tau. So but this x1, x2 is a Bernoulli process, right? It's a Bernoulli process. Oh. It's a Bernoulli process with probability P. With probability P, right? So P is the probability of arrivals, which is their probability of success, right? So okay, so what does that mean? That means your, so thus L tau is the number of success, which is the arrival there, okay? Success uh, in tau times, okay, of the Bernoulli process with probability P. Clear? So now I already know that how this is, I mean, what are those things. So now so this the so the moment generating function for say xi, so they are IITs, right? So they have same memory function. So let me write down mxi of say s. So how they look like? So they are Bernoulli random variable, right? And Bernoulli random variable. So this is Bernoulli p. So the one function, now you recall this is already done. So this will be 1 minus p plus p into e to power s. So this is the homogeneous function, right? Each of those xi's. Clear? And now also recall that because L equal to L tau is sum of this exercise where n tau is random variables. So L tau is what? So L tau is the sum of random number of random variables, right? So we can say that as L tau is a sum of random number of random variables, random number of random variables, random variables we have. So what is the property? That also we learned in the previous one of the previous lectures. So the moment function of L tau at S will be what? So this will be nothing but expectation of the moment generating function of that exercise, and then this to the power this in tau, okay, expression of this. Okay, so this is already proved in our one of the previous lectures. So the margin function will be this, and now we need to calculate now these values. What is this value, right? So and also note that this in so note that the so PMF of the property mass function of n tau is given by how this property mass function look like. So this is P n tau at say k or n. This is given by lambda. This is a Poisson distribution with parameter lambda tau. So this power n and then e power minus lambda tau by factorial n, right? And n, where n can be 0, 1 and so on, 2, so on, right? So this is you know, right? Thus from this formula, so this formula 1, so thus from 1 what we get? We get that the moment generating function L tau of S is summation over, so this is function of random variable, so mx s to the power, suppose they are taking the value n tau is taking value n, so you can write down that n equal to 0 to infinity and n tau taking value n, and then probability that n tau taking value n, right? Probability mass function of n tau. Okay, and now this is, we write down this is 0 to this. What is this value? So this value is so maybe we'll write down later, so just keep it right now. Same here, mx. See, so I'm writing mx for m size because they are IITs, right? So size are IITs. So I'm writing mx. So mx of s or n, and then this is what? This is lambda tau power n e power minus lambda tau by factorial n, right? Now what is this? So this is e power lambda tau independent of n, so you can take outside, and inside sum you can write down as n equal to 0 to infinity lambda tau into mxs whole to the power n by factorial n. Clear? Now similarly, now it is also a exponential series, you can easily find out, and thus it is nothing but e power minus lambda tau into exponential e power what happens? So e power lambda tau to mx of s, right? And thus you can write down e power lambda tau time mx is minus 1, and now we put the value of mxs. This is uh, already known, so this is 1 minus p plus p power e power is minus 1. Now minus 1 plus 1 get cancelled, and then p, take p outside, so it becomes lambda tau p into e power is minus 1, right? And see, now we can easily find out that this is uh, so this is the moment generating function of what? So this is my function of a Poisson random variable, right? Of a Poisson random variable, random variable with parameter lambda tau p, right? But tau is the length of the interval, so thus the local process is a Poisson process with uh, arrival rate. So what is the arrival rate then? It is nothing but lambda into p, because tau is the duration or length of the time. So lambda p. So what do you have? So then so you have local. So original process you break into local and two processes, right? Local process and another process, okay? Not local process. And so this is probability p, this is probability 1 minus p, then this is also Poisson, so then this is also Poisson with lambda p parameters, okay? And now you can easily find out that if this is process of lambda p parameter, then what happened to the other one, okay? So this is process with lambda 1 minus p parameters. Clear? So this method is a rigorous mathematical method to prove that splitting of Poisson process is possible. You can do by another method also. So, but I will not tell you in general. But I just want to give you third proof. So instead of number of arrivals, you can talk about the time intervals, right? Interarrival times. That also you check that interarrival times t1, t2, okay? So by that also you can do it, because these interval times are what? They are follow exponential random variable, right? And you can so fast you can do so fast interval times, so that may be t1 plus t2 and something, say tk. These 1, 2, 3 are not the local arrivals, the kth one local arrivals. So by this also you can do it, because they are all t1, t2, t3. This is first arrival, second arrival. You can break into Bernoulli process. So the sum of geometric, okay, and then you do the same process. You apply a moment generating function, and you can find out the same answer, right? Okay, so this is another one. So this is homework. Um, you solve these problems. Uh, solve these with moment generating function of this interarrival times. Okay, the same similar method will work. Okay, now there will be a, so similar to Barnum process, you have another process, another thing called merging, like so merging of a Poisson process. So first you have learned splitting, like one thing you just split it, and then suppose you have two process like these, and these, something like that. These. Can you kind of merge those two things and find out one process? The answer is yes. So it is coming here, it is coming there, it is coming here, and this is coming there, like that. Okay. So this is merge process. Okay, so what does that mean? So for example, same example I am going to now give you. So say Chandigarh GPO. So GPO Chandigarh. Now they are receiving say so letters with one process, and then packages. Okay, this is letters and some packets. Okay. Some give packets, other thing, right? Now question is that if you merge it, so now you will take the total arrivals, right? This is letter arrival of letter, this is arrival of packages. Now this is total arrivals. So total arrivals is Poisson process or not? So again, so these first two properties of are similar, obvious. So this independence, independent. This is you check it at home. Independence, dense, and time homogeneity. Homo. These are, you just check it. It's obvious. Now the third property, this small interval probabilities. Probabilities. Okay. So how do you check it? Small interval probabilities. So you see that. Okay. So, yeah. So this is masked process. Now small interval probabilities. So when you are marching, suppose you are keeping it probability with probability, say okay, so this is originally it was rate lambda 1 and this is rate lambda 2. So you would like to know that what is the rate of this process, the marched one, right? So so let lambda 1 lambda 2 be the arrival rate of the original two processes. Okay. Now for March process, you want to find out whether these probabilities of zero arrival. So this is, let me write M means March process in the time length of delta. Okay, what is this probability? So you see, this is approximately what? So zero arrival means what? Zero arrival means that in the first there is no, in the time length of delta there is um, there is no letters arrival, no package arrival, right? Nothing. So kind of this delta. There is no letter, no packet arrival, right? So so what does that mean? So that means this is approximately this is equal to probability that so this is probability 1 means the first process, lambda, I can write down lambda 1, 0 delta into probability this was 0 delta, right? And then you know that for both the thing this is equal to this, but you know that this is approximately lambda 1 delta plus higher order term, so that's why I said approximately. Okay, and this is also 1 minus lambda 2 delta approximately, right? So approximately if you multiply it, then you will have 1 minus lambda 1 plus lambda 2 of delta, plus higher order term. So higher order terms I am not writing because this is also tends to 0, right? So what does that mean? That means is this probability is approximately 1 minus lambda 1 plus lambda 2 delta. Now see, this satisfy the third property of small interval times, and also the other probability is find out the probability of March process, that one arrival. So one arrival means what? One arrival means either in the first process there is one arrival, and second process there is zero arrival, or in the first process there is zero arrival, into second process there is one arrival, right? But again, this is approximately one arrivals is what? The first process, this is lambda 1 delta into zero arrival 1 minus lambda 2 delta, plus here lambda 2 delta into 1 minus lambda 1 delta. Okay, now we multiply this, you see uh, uh, this higher order term of delta. So this is nothing but lambda 1 plus lambda 2 of delta, okay, and plus higher order term, right, of delta square. But this is tends to 0, this quantity, so you can write down this approximately lambda 1 plus lambda 2 of delta. Okay, now see, this is also, this satisfies the third property of the small interval time. So thus the March process, what is the conclusion? So the March process is again a Poisson process with arrival rate lambda 1 plus lambda 2. Okay, clear? Okay, so thus so this is kind of the main topics of Poisson process. So I will stop here, but now let me ask one question, quiz question. So maybe I can ask a simple question. So, and you need to understand my previous lectures to solve this problem. So quiz 6. So show that. So the number of, and you need to send this thing by 25th of March 2020. Okay, so the number of okay, so number of solutions or other number of answers of quiz we received by me this number follows a Poisson process with a rate of say 50 per day on the deadline and uh, 10 per day on the next day of the deadline. Okay. For example, on 25th I will have received more solution, then there will be 26, 27. So I'm just assuming that 50 and 10 for 2 days. Okay. Now my question is that what is the total PMF of so question. So this is I'm giving information. Then what is the PMF of the total number uh, total number of um, received solution uh, between say um, mm, 11 p.m. to 11 p.m. 25th 4 2000 to 1 p.m. 1 a.m. 2640. Okay, so I'm asking you that. Okay, 11 p.m. 25th the deadline, right? So from 11 p.m. to 26th 1 a.m. in between that I am receiving many such solution, right? So I'm asking what is the PMF of that. Okay, so this is the question, and this ends today's talk. I hope you are enjoying my talk, and if you have any question, please uh, write down on the comment section. I would love to answer those questions as soon as possible. Okay, so goodbye for now.